two times each value of this basis of some vector space. So if I say, for example, if I want the first u1 which equal to e power x, if I want to get the linear transform of the first vector, I will have to get y1 double dash. So in order to get y1 double dash, I will have to differentiate y1, which is e power x, 2 times. Okay, let's do it 2 times. So the first time, or the first derivative, will give you like this. So u1 dash will equal to e to the power of x. Differentiating once more, you will have y1 double dash, which also e to the power of x. Now I will try to get the linear transform of u1, which is u double dash plus u, and that's equal to e power x, which stands for the second derivative, plus the image of the main function, which is e power x, that's 2e to the power of x. So this is the image of u1 after your linear transform. I can do exactly the same for u2, which is e power negative x. Once more, once you try to differentiate, you will have u2 dash, which is going to be negative of e power negative x. And u double dash will be e to the power of negative x also, by positive. So getting the linear transform of u double dash will equal to e power negative x, plus the main function, which is u, once more e power negative x. And this will leave you with t e power 2e power negative x. So this is one of them. This is the image or the t of u1. This is the t of u2, and similar for u3. But here u3 is sine of x. So now I will have u3, which is sine x, differentiating, which is going to be a cosine of x, differentiating once more, so it's going to be a negative of a sine x. Now I will try to get the linear transform of u3, which is going to be u double dash, which is negative of a sine x, plus u3, which is sine of x. The result is equal to 0. So now the transform of u3 is equal to 0. Similar manner for t of u4, it's gonna be a 0 also with the same steps. So all of these steps is in the sake of finding the corresponding matrix that I will need to find its eigenvalues and eigenvectors. So it's stated here, this is u1, u2, u3, ex, e minus x, sin x, sin x. Start differentiating each one of these spaces 2 times. Then use your linear transform in order to get the results. Here we go. I will go with you step by step. So this is u1 once more. It's about e of x. So getting the first derivative, which is e power x. The second derivative, also e power x. Performing the transform, which will lead you to 2e power 2x. Similar manner, exactly, for e power negative 2x, it will give you the same results, which is 2e power negative x. Now for sine of x, differentiating once is going to be cos, sine x, differentiating twice is going to be negative sine x. If I use my linear transform, the result will be negative sine x plus sine x equal to 0. So it's exactly the same as I told you here, it's 0. Similar manner for cosine of x as a transform. Now for the e, which is going to be moved to using this linear transform, this is going to be the results for t e power x, t e power negative x, t over sine x, t over cosine x. So taking these values and trying to put them in the basis of the image, it will lead you to have the following. Okay, let me write it this way. I believe it's going to be much easier. So let me give this clarification. So after your linear transform, you will have the following. If you remark, I will have, after linear transforming. So I'm talking now about the image. The first one is gonna be 2e power x. The second one, t e power negative x. The third one is 0, and the fourth one is 0, which stands for 2 of a u1, 2 of u2, 0 and 0. And this will lead to the following span, which is 2 and triple zeros. For u2, it's gonna be 0 u1, 2 also for u2, and the zeros for u3 and u4. For both u3 component or the image and u4 image, all of them will be complete zeros, as you can see now. And this is the span that I'm telling you about. So our matrix that we will use in order to get these eigenvalues, it's gonna be 2 triple zeros. Then I will have 0, 2, and double zeros, as I told you. The third column will be exactly the same, and the last one will be also the same. This is the matrix that we will use in order to get your eigenvalues. This is what I'm telling you about. It's 2, all the zeros, same for second column, and the third and fourth columns, they will be exactly the same. Now, I will try to get these eigenvalues. So simply, all I have to do is subtract negative lambda from each one of them, similar to what we did before. So now, also to be sure that you understand me correctly, I will go through my characteristic equation. So this is going to be the value of the determinant. This is minus lambda, this is minus lambda, this is minus lambda, minus lambda, which is going to result to, I have lambda square times 2 minus lambda equal to 0, with an algebraic multiplicity of each value of these eigenvalues. So the first value is going to be 0, and with an algebraic multiplicity of 2. The second also will be the same, lambda 2 equal 2, with algebraic multiplicity of 2, as you can see. Then, if I want to get the, to continue, so this is 0 and 2 for the eigenvalues, eigenvectors or corresponding eigenvectors, this is going to be the set corresponding to 0, and this is going to be the set corresponding to the other value, which is minus 2. Of course, the 1 and 1, this is for, with respect to the first basis, the basis is going to be sine of x. This is cosine of x. For 1 and 1 is going to be e power x, e power negative x, as you can see for the eigenspace of this eigenvalue problem. This is also very interesting proof. He wants you to show that A and A transpose, they will have same characteristic polynomial. And this is really actually very simple, because it's related to the symmetric properties of determinants mainly. So if you remember once more, this is the characteristic equation that we are using in order to get the eigenvalues. So if I want to get the characteristic equation corresponding to the symmetric matrix, it's going to be AT minus A minus lambda I equal to T. So this is mainly going to be the form of the characteristic equation relative to the symmetric matrix. So it's going to be AT minus lambda I. As I told you, remember, okay, the symmetric properties of the determinants, that A determinant equal to X transpose. And also for the I, if you have a unit matrix, its transpose is exactly the same. And these two properties means that A transpose minus lambda I, it's exactly the same as A minus lambda I transpose. And this is final result if we take advantage also from this property once more, we've said it previously, so you will have that determinant of A transpose minus lambda I equal the determinant of A minus lambda I to the power of T equal the main determinant, so it is proved. For the remaining, you will have also a couple of problems, which is very, very simple. This is similar to the problems that we solved previously 1 million times. This is a 2 by 2 symmetric matrix. So it is easily can be we can find the eigenvalues, eigenvector, and get also normalize the model matrix and blah blah blah, exactly like the first lecture in our course. What I want to add is the quadratic part. I want to review with you the quadratic part for this problem. So the quadratic part for this problem, I can do it really very easily. All I have to do is to put x and y here, take this symmetric matrix, which is actually 0, 0, 2, and y, and then I will multiply it by x and y, exactly as we did previously. I will take the coefficient of, or the entry 1, 1, and I will put it in front of x squared. I will take the value of 2, 1 multiplied by 2, so it's going to be a 2 times 2, this value with the sign, times x and y, and then finally I will take this value, which is 0, multiplied by y squared. This is the quadratic part that's asking about here. So this is the quadratic form of A, defined by A, which is going to lead to a form of an xy for the quadratic part. Of course, it's a positive definite quadratic form, because simply, it's not going to be, because simply if you try to get your values, for the values of the eigenvalues, you will have the following: minus lambda, 2 and 2, minus lambda equal to 0, which will lead to lambda squared by negative, minus 4 equal to 0, which means lambda squared plus 4 equal to 0. So once more, it's a negative lambda times negative lambda, which is going to be positive lambda squared, minus 4, so you will have lambda squared minus 4, which is the difference between two squares, so easily can be factorized to lambda 2, and the negative 2 equal to 0. This is positive, so one of them will equal to 2, the other one will equal to negative 2, and it is indefinite, so definitely this part is not correct. I want you to review these problems. It's really very direct, so this is exactly the same steps as we have performed before. This is the solution: lambda 1 equal negative 2 and lambda 2 equal positive 2. These are the main steps that we will go through, as you can see, in order to get all the values. Here from this part, I will have just only for x or y. The quadratic form defined by A is one positive definite, as I told you. You have one of them positive and the other is negative, so it's indefinite quadratic form. Guys, these problems also are exactly the same steps and everything. Now you have the quadratic form. Also, you can regain your matrix by a similar manner. So please try to go through them, and if you have any questions, please don't hesitate to send it to me. I'm here for you in all times, so if you need anything or any questions, please don't hesitate to contact me. Thank you very much, appreciate it, and enjoy your day. Thank you. Bye-bye.